Welcome to the Explainer. Now, today, we are specifically talking to all you project managers out there. Consider this upcoming content your personal playbook. If you've ever felt this kind of frustrating disconnect between your feature requests and the way your engineering team actually thinks, well, this Explainer is going to bridge that gap for sure. We're going to dive right into the technical mindset and show you exactly how system design works from the ground up. The goal here is to empower you to write better specs, ask the right questions, and ultimately build much better software. Okay, let's dive into this. I want to hook you right away with this absolutely fascinating quote from Linus Torvalds, the creator of Linux. He basically says that the real difference between a good and bad programmer comes down to prioritizing data structures over code. Now, as a project manager, this is a massive paradigm shift. It means successful software isn't just about your team writing lines and lines of code. It's fundamentally about how data is organized, stored, and operated on. If you understand the data, the code naturally follows. So here is our game plan for today. We're going to hit the fundamentals of software, defining inputs and outputs, solving problems with subproblems, interfaces versus implementation, and finally, measuring algorithm efficiency. But hey, keep your ears peeled for Section 2. That's going to be your absolute secret weapon for your daily PM duties. All right, Section 1, the fundamentals of software. Before we get into the really advanced stuff, we need to establish a shared vocabulary for the basic building blocks of any digital project. We hear the word algorithm tossed around in literally every kickoff meeting, right? But let's strip away the technical mystique for a second. An algorithm is simply a step-by-step procedure designed to solve a specific problem or perform a particular task. That's really it. It's just a set of instructions to get a job done. The real magic isn't the fancy term itself. It's the strict rules those instructions actually have to follow. And building into those strict rules, these are the essential characteristics of any algorithm. It has to be finite, meaning, thank goodness, it eventually stops. It must be definite, with unambiguously defined steps. It has to be effective, meaning it can actually run with the resources you have on hand. It takes inputs and produces outputs. It must be correct. And finally, it must be deterministic, meaning the same input should always yield the exact same output. Burn the words definite and deterministic into your mind. A good algorithm leaves absolutely zero room for ambiguity or guesswork. To ground this highly abstract concept into a relatable process, let's think about making a simple cup of tea. Your inputs are the tea bag, kettle, water, milk, and cup. The algorithm is the steps. You boil the water, pour it, steep the tea, add the milk. And the output? A perfect cup of tea. But remember that definite characteristic we just talked about? If this were a true computer algorithm, these steps are actually terrible. I mean, how much water? What if I want it stronger? How much stirring? To a machine, ambiguity breaks the whole system. And this is exactly why your project specs need to be incredibly precise. Moving right along to Section 2, defining inputs and outputs. This brings us perfectly to the core focus of this explainer. This is the ultimate requirement gathering step that PMs must master to ensure effective software design. So here's a question to kind of challenge your usual project kickoff habits. Why identify inputs and outputs before writing a single line of code? Why not just let the engineers figure it out as they go? Well, the crucial point is this. It is absolutely imperative to specify inputs and outputs before writing an algorithm, because they define the signature of the code. The variables used throughout an entire program hinge on this. Honestly, this is the golden rule for you as a manager. Inputs and outputs form the fundamental contract between what the business wants and what the engineers will actually build. Before getting into the technicalities of how the algorithm works, you must define exactly what data goes in and what data must come out. Let's put this into perspective and compare these two examples. See how drastically the signature changes based on the business problem being solved? If the problem is just reversing a list of items, the input is simply the list, and interestingly, the output might actually be none if we're just modifying it in place. But look at finding a shortest path. The input requires a weighted graph, a start node, and a destination node. The output is a highly specific list of nodes representing that path. If your spec just casually says find the shortest route, but you don't define that the input must include a weighted graph, your engineers literally can't write the function signature. Okay, Section 3, solving problems with subproblems. Let's transition over to how engineers take those massive project requirements with your clearly defined inputs and outputs and actually start building them out. Imagine trying to route a path from Helsinki to London. A computer can't just magically know the shortest way. To a machine, a complex problem like this requires routing through smaller, individual city connections. It's like a giant puzzle. It has to check the distance to one city, then to another, and so on. We call these smaller chunks subproblems. And this maps perfectly to the 5-step problem-solving process your developers use every single day. First, they specify the problem using those inputs and outputs you gave them. Second, they split the problem into smaller subproblems. Third, they solve one subproblem at a time. Fourth, they combine those solutions back together. And fifth, they test it. And they test it using both realistic and totally ridiculous cases. Because, as we all know, users will always find the most bizarre ways to break software. Understanding this process really highlights how your big PM goals are systematically broken down into manageable developer tasks. Which brings us to Section 4, Interfaces versus Implementation. We're going to look at the concept of abstract data types now. This is going to really help you understand exactly where your responsibilities end and the developer's responsibilities begin. Think of an abstract data type, or ADT, as a literal wall. This is a concept that perfectly visualizes a strict boundary. On one side, you have the program asking to perform operations, like add, remove, or find. On the other side, you have the data structure itself. That ADT wall in the middle isolates the concrete data structure from the program that's trying to use it. I love to think of this as a boss versus worker dynamic to make it perfectly clear. The abstract data type is the boss. It's the interface. It's logical. It defines the functionality or what to do. For example, you, the PM, ask for a queue system so users can wait in line. The data structure is the worker. It's the concrete implementation. It executes the functionality or how to do it. The engineer decides whether an array or a linked list is the best worker for that specific job. You define the interface, they handle the implementation. Finally, Section 5, Measuring Algorithm Efficiency. Let's open our last section by addressing a very, very common PM headache: why engineers might push back on certain feature requests when the project scales. It all comes down to measuring performance. So engineers use something called static analysis to determine complexity. They literally write out how much work each part of the code takes. Basic operations take a constant unit cost of time, but the total amount of work heavily depends on the input size. Let's say your new feature requires the code to loop through a user's entire history, and that history grows from 10 items to 10,000 items. That loop multiplies the cost of the instructions. What seems like a super simple feature request to you might actually trigger thousands of hidden loop operations in the background for them. And this explains exactly why your team might say no or offer an alternative. At the end of the day, there are unavoidable trade-offs in software. You constantly have to balance time versus space. If you want something to run incredibly fast, it might require taking up massive amounts of memory space. You also have to balance generality versus simplicity versus performance. Every single technical choice involves a compromise. Understanding these trade-offs helps you manage stakeholder expectations when they come asking for a feature that is somehow both blazing fast and infinitely complex. We've covered the fundamental building blocks, the critical nature of inputs and outputs, how problems are broken down, the boundaries between interface and implementation, and the reality of computational trade-offs. I want to leave you with this provocative thought to take right into your next sprint planning session. Do your project specs clearly define the inputs, or are you just leaving the signature to chance? The success of your next big software launch depends entirely on how you answer that question. Go out there and start defining those contracts.